Hey Team Physics, welcome back from Thanksgiving break. Tonight, you are going to be jumping into the study of rotational motion. Now, as you might recall, we have studied other types of motion before this, linear motion being one of them. And linear motion described motion in one direction. For example, a ball rolling across a table, or a ball being thrown up in the air. These are both examples of linear motion. The other type of motion that we've talked about in class is projectile motion. And this is both motion side to side and up and down. So for example, a ball being thrown not just straight up in the air, but at an angle. This is an example of projectile motion. Or a ball being kicked off a cliff. That is another example of projectile motion. And so now rotational motion, as you might imagine, is not things moving back and forth or up and down, but something moving in a circle, something spinning. And this is important because it helps us understand, for example, why we experience both day and night on the Earth, and why we can spin a bucket full of water over our heads without getting doused, or even how we could simulate Earth's gravity out in outer space. So rotational motion will help us understand all of those fun things. So before we begin our discussion of rotational motion, there are a few vocabulary words that you need to become comfortable with. So to start us off on that, let's talk about the Earth. So here we are. Here's the Earth. And as we all know, the Earth is spinning. So this spinning is called rotation. It's a turn about an internal axis. Which brings us to our second word that we're going to define, and that is axis. So as you see right here in this picture of the Earth, the axis is demonstrated by this needle-like thing going straight down through the center of the North Pole and out the South Pole. And an axis is a straight line around which rotation takes place. Okay, great. And now if you can imagine me as a tiny little person perched somewhere in Southeast Asia somewhere on the Earth. As the Earth rotates, I revolve. So the Earth is rotating around an internal axis, and I am revolving, which means I am turning about an external axis. So the axis is not within my body. If I personally were spinning, I would be rotating, but I'm standing on the ground, revolving around its axis. Okay, and if we want to know the rate at which I am turning around the Earth, and back at which point, for example, I will start in Southeast Asia, and I will stay in Southeast Asia, but spin all the way around the Earth as the Earth turns. That's called rotational speed, and it's the number of rotations per unit time. Now with the Earth, we know the Earth completes one full rotation every single day, so the rotational speed of the Earth is one rotation per 24 hours. Now, rotational speed is one thing, measuring the number of rotations, or the number of revolutions that occur within 24 hours, which is one for the Earth. Linear speed is another thing, and linear speed measures the distance per unit time. I'm going to write that down here. And now, this is probably the trickiest concept that you are going to learn tonight in this screencast overall. So rotational speed, you should see very quickly that it doesn't matter where on the Earth I'm standing, my rotational speed is always the same. So it doesn't matter if I'm standing in Southeast Asia, or right next to the North Pole, or in Europe, or right here in Connecticut. The Earth still rotates at the same speed. One complete rotation, every 24 hours. Now, however, my linear speed on the Earth is variable. It depends where on the Earth I'm standing. And this is kind of confusing, so I'm going to break it down for you very simply. So let's start getting another picture of the world. Okay, so here's our second picture of the world. And let's imagine we've got someone standing on the equator, right here, somewhere down in South America. They're on the equator. And someone else standing up here in Connecticut, right about here. So, So the Earth is spinning, and both these people are experiencing the same rotational speed. Number of rotations per unit time, 1 rotation per day for both of them. However, they're experiencing different linear speeds, and I'm going to explain to you why right now. So imagine we were to cut the Earth right at the equator where this person is standing, right in half right here. We'd be left with a circle looking down from the top. That's, say, approximately this size, right? And the circumference of the Earth at the equator is about 40,000 kilometers. So our little person standing at the equator is covering a distance of 40,000 kilometers per revolution. So this is over the course of one day. Okay, awesome. And now let's go to our little guy up in Connecticut. And we see here that if we were to cut the Earth all the way around in a big circle, we'd get another circle, but it wouldn't be quite as big as the circle of the person when we cut the Earth at the equator. So in fact, about around where we are, the circumference of the Earth is about 27,000 kilometers. So this person at the equator is traveling a distance of 40,000 kilometers per one day, and the person standing in Connecticut is traveling 20,000 or 27,000 kilometers in one day. So yes, people at the equator are moving faster around the world than people who are living in Connecticut. So, I'm going to just bear with me for a second. I'm going to move the circle inside here. And so, you should know from this, so this is linear speed, which is also called tangential speed. And tangential speed or linear speed has a relationship between both the rotational speed of the object, so in this case the rotational speed of the Earth is rotating at a rate of, or revolving, you're revolving around the Earth at a rate of 1 time per day, and also a relationship from the radial distance from the axis. So if we add in, superimpose our axis down here, then we see that our guy on the red circle, our guy in Connecticut, is closer to the axis than our guy at the equator. So we can say here that tangential speed is directly proportional to both radial distance, the distance from the center of the circle or the axis, as well as the rotational speed of the object. So if the Earth were to start rotating faster, then the tangential speed of both these people would increase, or the linear speed. Additionally, if the Earth were to get wider or fatter and rotate at the same rate as it is currently, the person who's at the equator would be going faster. So I'm going to write that down. Tangential speed is proportional to radial distance and rotational speed. So to summarize, In any rotating system, all parts have the same rotational speed. However, the linear or the tangential speed is going to vary, and it's going to depend on both the rotational speed and the distance from the center or the axis of rotation. So, that is all for today's screencast, and I hope this was useful to you in completing your homework. Okay, see you all tomorrow.